So we have this AC equivalent circuit. Let's see how we can find out what are the currents flowing through this. Now we have a transistor and there are some AC currents flowing through it. So IB, IC, IE. And as I mentioned before, these are AC currents we're dealing with, so we denote them with small letters rather than with capital letters. Now there is a way of simplifying what this transistor would look like. In a simplified form, you can write it like this. So you have your IB, IE, this is a resistance RE prime, and here you have a constant current source IC. Let me explain what this means. You have some base current coming into your transistor, and your collector makes sure that there is a constant current flowing through your transistor, and that current is what we are calling IC, the collector current. There is an internal resistance within the transistor. The transistor's internal resistance is what we denote by Re prime, and Re prime is given by Vt over IE. IE is your DC emitter current. Vt is what is called the thermal potential inside your internal diodes, and this has the value 25 millivolts. Where does this number come from? That comes from solid state physics. So if you look at the internal physics working of how a diode works, you can derive this number 25 millivolts. It's a temperature dependent quantity. 25 millivolts is its value at around room temperature. So at usual operating conditions, Vt is almost always 25 millivolts. So this actually is this Re prime equals 25 millivolts by IE. You can just consider this as canon for the sake of our course. So this is a simplified form of what our transistor will look like. So now once again, let's draw the AC equivalent circuit, but with this simplification in place. So now our circuit looks like this. We have our input Vs, we had R1 parallel R2, then we had our transistor, which we are replacing with this simplification. What else did we have? We had RC, which was RC parallel RL, and here is where we are taking the output. Now when we draw the circuit like this, this kind of description is called the T model. It's a T model of simplifying a transistorized circuit. This is not the only possible model available in the market. If you look at Malvino's book, they discuss what is called the pi model. Or if you look at some other literature somewhere, they'll also have something called a hybrid model. So there are lots of different ways of simplifying a transistorized circuit. This is just the one that seemed simple to me, and that's why I'm discussing this with you. Now once this is done, life is easy. We are almost finished with analyzing our AC circuit. What do we want in the end? We want V out and we want V in. V in is the voltage which is going into the base. VB, and VB is potential over here is IE RE prime. And what is V out? V out is the potential over here. Now there's the collector current flowing through this. So V out is just IC RC. So then the voltage gain, which we denote as AV, is just V out divided by V in, which is ICRC divided by IERE prime. But if you remember, IC and IE are almost the same because IB is typically very small. So AV, the voltage gain, is just RC divided by RE prime. So this is the formula for the voltage gain that you get from a transistorized CE amplifier. Let's look at one numerical example to see how exactly one solves this. Okay, let's draw this circuit again. Plus VCC, voltage divider, collector resistance, emitter resistance, and the capacitor over here. We'll put one capacitor at the input. We'll put one capacitor at the output. And we'll put one load resistance. So this is our transistorized CE amplifier. Let's put down certain values for all these parameters. R1 I'm calling 8 kilo ohms. R2 is 2 kilo ohms. RC is 3 kilo ohms. RE is 1 kilo ohm. RL is 6 kilo ohms. So how should we do this calculation? Let's again start with the base, collector, emitter. So voltage at the base you get from the voltage divider circuit, which is VCC R2 over R1 plus R2. How much is VCC? 15 volts, okay. So this is 15 times R2 is 2, R1 plus R2 is 10. So this is 3 volts. Then next I want to find out what is the emitter voltage. So VE is VB minus VBE from here. So this is 3 minus, let's say this is a silicon diode, so I'll say 0.7 volts for VBE. So now this becomes 2.3 volts. Now that I know the voltage at the emitter, I can find out what is the emitter current. So emitter current is just the current flowing through RE. So that is VE divided by RE. VE is 2.3 volts. RE is 1 kilo ohm. So this is 2.3 milliamps. So then IC also is roughly 1.3 milliamps. By the way, how much is every transistor has its own characteristic value of beta, the current gain. So let's say for this one beta is 100, then what do you think the base current will be? So IC is beta IB. So if beta is 100, then IB is going to be IC divided by 100. So 23 microamperes. So that's how small the base current can get. Okay, anyway, we have IE. That is all we wanted. Now in the AC analysis, I have to draw that circuit again. Okay, let's draw it again. Yes. So this is our AC equivalent circuit. So R1 parallel R2 is what? 8 parallel 2, which is 16 over 10, which is 1.6 kilo ohms. The AC collector resistance RC is, what is RC and RL? 3 and 6. So 3 parallel 6, 3 times 6 18, 3 plus 6 9, so this is 2. How much is RE prime? RE prime is 25 millivolts divided by the DC emitter resistance. So 25 millivolts divided by 2.3 milliamps. So this is going to be something like 10 ohms roughly. How much is it in my calculations? 10.86 ohms. So then the gain that we get in the end is going to be RC over RE prime. RC is 2 kilo ohms, RE prime is 10.86 ohms. So this is going to be something like 184 approximately. So for this CE amplifier, you get a gain factor of 184. So for example, if you put in a 1 millivolt input signal, if you put in an AC input of around 1 millivolt, what this means is that your output is going to be 184 millivolts. So that's why this is an amplifier. It amplifies your signal. One thing that I should remind you over here, again it would have been good if I had that circuit with me. Never mind. Suppose as you increase your input voltage, the base current increases. Since the base current increases, your collector current increases, and as your collector current increases, your collector voltage decreases, because VCC is ICRC plus VCE plus VC from Kirchhoff's voltage law. So increasing IC will decrease VC. But VC is, collector is where you're taking your output. So basically, you increase your input, you decrease your output. So what this means is that your input and your output are out of phase. Means it is amplifying, but it is amplifying with the wrong sign. So if this is your input, then your output is amplified, but it is the other way. Get it? So this is called an inverting amplifier. Let's talk about the load line a little bit. So the DC load line equation was given by VCC equals ICRC plus VCE plus IERE. Or if you are willing to assume that IC and RE are roughly the same, then we will just say IC times RC plus RE plus VCE. So now if I plot the characteristic, the output characteristic, you'll get some load line like this, which comes from this load line equation, where this, as we discussed last time, when IC is 0, so this is just VCC, and this point is where VCE is 0, so this is VCC divided by RC plus RE. But now, when you're talking about AC signals, RE is as good as not there. Why? Because we had put this bypass capacitor across it. So as far as AC signals are concerned, this RE over here is 0, and so for AC we get a different load line equation, and it looks something like this. So this is called the AC load line equation, and this is called the DC load line equation. And the intersection of these two lines is what we call our Q point. At the end, I want to talk about power. So far we have talked about voltage gain. We defined the voltage gain as output voltage divided by input voltage. Now we want to talk about the power gain. So this is voltage gain. We'll define power gain in a similar manner. So this is output power divided by input power. Now there are some special units in which we can calculate the output, because typically these gains are very large numbers, like factors of 100, 1000, 10,000 and so on. So it makes more sense to try and look at them on a logarithmic scale. So we define a unit called bell. So AP in bells is defined as log 10 of P out over P in. Or if you want to work in 1/10 of a bell, which is called a decibel, or it is given in, it's denoted as dB. This is 10 times of the bell. Now if you remember, power typically goes as V square over R. So for a given resistance, if you want to define AP in decibels, is given by 10 times log 10 V out square over V in square, which is 20 log 10 V out over V in. And the last thing that I want to go to, again in terms of this power gain, is what is called bandwidth. It's a commonly used term. You have probably heard of it in the context of some radio communication and so on. Normally, if you look at an amplifier, the gain of the amplifier is dependent on what is the frequency of the signal that you're feeding. It's not constant across all frequencies. So if I plot the power gain in decibels versus the frequency. So ideally, of course, it would be constant. It would be independent of frequency, but that is not the case. What you really have is what looks something like this. So it's flat over some intermediate range, but for very small frequency and for very large frequencies, the gain will be less. So what we do is, suppose this maximum value is, let's call it AP max, and then you check at what level does this become AP max minus 3. So basically we want this fall to be 3 decibels. Let me rewrite this. So this upper one is AP max, the lower one is AP max minus 3. So it's a fall of 3 decibels from the maximum value. And then we see for what frequencies this happens. So let's call this frequency F1. Let's call this frequency F2. And then this F2 minus F1 is what we call bandwidth. So within this range of frequencies, your power gain is going to be within 3 decibels of its maximum value. So we say this is an acceptable range for operating your amplifier. So you can do a quick calculation if you want AP max minus AP, let's call this as AP cutoff. So AP max minus AP cutoff is 3. But AP max minus AP cutoff is just 20 log 10 AV max AV cutoff. And from this, if you just solve this equation, you'll find that the AV cutoff is going to be around 0.707 times AV max. So basically the cutoff is where your voltage gain has dropped to around 71% of your maximum voltage gain. Then within those frequency ranges is what we call bandwidth, and that is what is considered a good value of frequency within which you can operate your amplifier.